Imagine a place where time and space distort and twist, where the laws of physics as we know them cease to apply. Welcome to the mysterious world of black holes. Black holes, celestial bodies so enigmatic, they've long been a riddle wrapped in a mystery inside an enigma. They are regions in space where gravity is so intense, so overpoweringly strong, that nothing, not even light, the fastest entity in the universe, can escape their grasp. These cosmic beasts are the remnants of massive stars that, once they've exhausted their nuclear fuel, collapse under their own gravitational force. The star shrinks and shrinks until it becomes a point in space with infinite density, known as a singularity. Around this singularity, a boundary forms, the event horizon, a point of no return beyond which anything that ventures in is forever trapped. Scientists have been fascinated and puzzled by black holes since their existence was first proposed. These cosmic oddities challenge our understanding of the universe, pushing the boundaries of our knowledge and comprehension. They're a testament to the power and mystery of the cosmos, an embodiment of the unknown that lies beyond our reach. They've been the subject of countless studies, theories, and debates. Their existence confirms the predictions of general relativity, yet they also highlight the inconsistencies between this theory and quantum mechanics, two pillars of modern physics. Black holes are not just distant astronomical phenomena. They're crucial to our understanding of the universe, to our quest for a unified theory of everything. They're a key piece of the cosmic puzzle, a door to new realms of physics and cosmology. The question that has baffled scientists for centuries is, what's inside a black hole? It's a question that has led to some of the most profound and controversial theories in physics. Today we delve into the deepest corners of the universe to find out. Prepare for a journey like no other, a journey into the heart of darkness, into the enigma that is the black hole. Albert Einstein's general theory of relativity, published in 1915, opened our eyes to the concept of black holes. This groundbreaking doctrine painted a new picture of the universe, where the fabric of space and time could be warped and distorted by the mass of celestial bodies. Let's delve deeper. Einstein's theory predicts that matter can distort the space-time continuum around it. Imagine a bowling ball placed on a trampoline. The weight of the ball bends the trampoline fabric, creating a depression. Now, if we roll a marble around the edge of this depression, it will spiral inward, drawn by the pull of the bowling ball. This is a simplified analogy for how a star's mass warps the space-time around it, pulling in other objects. But here's the kicker. If the mass is compact enough, it can warp space-time so dramatically that it forms a black hole, a region from which nothing, not even light, can escape. The boundary of this region, the point of no return, is what we call the event horizon. So, what's at the center of these cosmic behemoths? The theory of relativity predicts a singularity, a point where density becomes infinite and space-time curvature becomes extreme. This is where things get really weird. At a singularity, our understanding of the universe breaks down. The rules of physics as we know them simply stop making sense. Despite its predictive success, the theory of relativity grapples with a significant limitation. It fails to explain what happens inside a black hole. It stumbles when it comes to detailing the extreme conditions at the singularity. The mathematics of the theory breaks down, leading to paradoxes and infinities that physicists find uncomfortable. But the theory of relativity fails to explain what happens inside a black hole. For that, we need to turn to quantum mechanics. Yes, the world of the incredibly small might just hold the keys to these cosmic giants. But that, dear listeners, is a tale for another scene. Quantum mechanics, the other pillar of modern physics, gives us a different perspective on what's inside a black hole. So let's dive into it. Quantum mechanics is all about the smallest particles in the universe and their weird, almost magical behavior. It's a world where particles can be in two places at once and can interact with each other instantly over vast distances. Now here's where things get really intriguing. Quantum mechanics has a fundamental principle that information can't be lost. It's a bit like the first rule of Fight Club, but for physicists. This seems to contradict the black hole singularity idea, where all information about anything that falls in is lost forever. But wait, there's more. Enter Stephen Hawking, one of the greatest minds of our time. He proposed a theory known as Hawking radiation. This theory suggests that black holes can actually emit particles. Now, you might be thinking, how is that possible? I thought nothing could escape a black hole. Well, Hawking radiation is not exactly something coming out of the black hole. It's a little more complex than that. You see, in the quantum world, pairs of particles and antiparticles can suddenly pop into existence and then annihilate each other. This happens everywhere, even near the event horizon of a black hole. Sometimes one of these particles falls into the black hole and the other escapes. To an outside observer, it seems as if the black hole has emitted a particle. Over time, this process can cause the black hole to slowly lose mass and eventually evaporate completely. But there's a catch. If black holes evaporate, what happens to all the information that fell into them? According to quantum mechanics, it can't just disappear. This contradiction between quantum mechanics and general relativity is known as the black hole information paradox. This leads us to a paradox. So what's the solution? Scientists have a brand new theory. Enter quantum loop gravity, a theory that attempts to reconcile general relativity and quantum mechanics. Picture this. Instead of a smooth, continuous fabric, space and time are composed of tiny, discrete loops, much like a piece of fabric viewed under a powerful microscope would reveal individual threads. This is the fundamental premise of quantum loop gravity, a groundbreaking theory that dares to challenge our understanding of the universe. So how does it work? Well, in the world of quantum loop gravity, the fabric of space-time isn't smooth, but actually granular, made up of these infinitesimal loops. These loops are incredibly tiny, around 1,000,000,000,000,000 times smaller than a single atomic nucleus. Now, it gets really interesting when we apply this theory to black holes. Remember the singularity, the point of infinite density that traditional physics can't explain? Quantum loop gravity does away with that concept. Instead, it introduces something quite extraordinary, known as a quantum bounce. According to this theory, when matter within a black hole collapses, it doesn't shrink into an elusive singularity. Instead, it condenses until it reaches a certain size, a size determined by the granularity of spacetime. But it doesn't stop there. Once it hits this size, the force of gravity becomes so strong that it's overpowered by the quantum effects of space and time, causing the collapsed matter to bounce back out. Imagine, if you will, a cosmic trampoline. The collapsing matter is like a person jumping high into the air and then coming down hard. The trampoline stretches to a point, then the tension becomes too much and it springs back, propelling the jumper back into the air. That's essentially what's happening in a quantum bounce. So, what does this mean for our understanding of what's inside a black hole? Well, it's mind-boggling to consider, but if quantum loop gravity holds true, then it suggests that every black hole might be a gateway to another universe. So, according to quantum loop gravity, inside a black hole could be another universe? If quantum loop gravity holds true, the implications are mind-boggling. It could mean that our universe, with all its galaxies, stars, and planets, might have been born from a black hole in another universe. Imagine that, a black hole, a region of space where gravity is so strong that nothing can escape, not even light, could be a cosmic cradle, giving birth to entire universes. This theory paints a picture of a multiverse, a network of universes connected by black holes, where each universe could be the interior of a black hole in another universe. It's like a cosmic Russian doll, with universes nested within universes. But before we set off to explore these other universes, let's remember that quantum loop gravity is still a theory in its early stages. It's an exciting prospect, a tantalizing glimpse into the possible structure of reality, but it needs more research, more data, more evidence. Scientists around the world are working tirelessly, using the most advanced technology and the most sophisticated mathematical models to test this theory and unravel the mysteries of black holes. While we may not have a definite answer to what's inside a black hole, our quest for understanding these cosmic giants is taking us closer to the secrets of the universe. Every question we answer, every discovery we make, brings us one step closer to understanding the grand, intricate tapestry of existence.